Welcome back. In this video, we continue our study of Chapter 1 and we move to Section 1.5 about subspaces or metric subspaces. So suppose that we have a metric space XD and we have a subset Y of X. Now, when we so D is a function of two variables in capital X. It's a function from capital X times itself into R. So when we restrict this function D to the smaller set y times y, we get a distance on the smaller set y. Okay, so that is denoted by d sub y. So d sub y is just d, but restricted to y times y. So when we equip y, capital Y, with this distance, we get a metric space. And so this is so we can call y equipped to this distance a metric subspace of X. Okay, so therefore, we can talk about open sets in Y, closed sets in Y, neighborhoods, etc. So all the concepts that we learn in any metric space or related to the notion of open set are still true, available for the smaller space Y. Okay, so but how to characterize, what is the relation between open sets of Y and open sets in the bigger space X? Okay, so for this we need a new notation. The ball in capital X of center small x and radius r will be just denoted by capital BXR. But the ball in capital Y of center x and radius r, if x is in capital Y, is the set, by definition, the set of all z, if you like, in capital Y, whose distance to x is less than r. Okay, so we'll distinguish between the ball in Y, B sub Y, and the ball in X, capital X, that you just denote by capital B. We can also write B sub X, but it's not necessary. Now, this ball in Y, if you go back to the definition, is just the intersection with Y and the ball in the bigger space, capital X. Yes, this is by definition. Okay, so here's the first characterization that gives a relation between the open sets of Y and the open sets in capital X. So if now A is a subset of capital Y, then A is open in capital Y, if and only if A can be written as the intersection of Y with an open set in the bigger space X. Okay. So like balls, actually. So I have to prove here two implications. Suppose first that A is the intersection of Y and an open set in the bigger space X. We want to prove that capital A is open in Y according to the definition of a metric topology. So we have to prove that every point small x in A, for every x in A, there is a ball of center X contained in Y, a ball in Y, of course. So if X is in A and A is the intersection of Y, so A is contained in O, right? Therefore X is in O. But since O is open in X, there is a ball in capital X with center small x contained totally in O. This is by definition. So I just take the intersection. So the intersection of BXR with Y is contained in the intersection of O with Y, and this is just A. Now BXR intersected with capital Y is just the ball, BYXR. So we found a ball in the smaller space, capital Y, of center small x, totally contained in A. And this by definition implies that since x was arbitrary, this means that capital A is open in capital Y. So this is half of the proof. Now, conversely, suppose that capital A is open in Y. So here we have to distinguish between open in Y and open in X, not the same thing in general. Okay, then by definition, for every small x in A, there is a ball in Y whose radius depends on x. So I denote the radius by r sub x, as you know. So because when x varies, the radius varies. Okay, so for each x in I, we have a positive number rx such that the ball in Y of center x and radius rx is totally contained in capital A. And this implies that A can be written as the union of all these balls in Y when x varies in capital A. And this is we encountered this idea before when we proved that a set is open if and only if it's in a neighborhood of all its points. How do we prove this identity? Double inclusion. Of course, for every x, by xr is contained in A, so the union is contained in A. And now conversely, let us take an element in capital A, call it small a. If small a is in capital A, then we can write that small a belongs to byARA, small ARA. Okay, so small a is in some of these balls, so it's in the union, so double inclusion. Okay, fine. And now take O to be the union of all balls in the bigger space. So here we have to distinguish between B sub y and just B. Okay, so O and A are not the same thing. Okay, because A is the union of balls in Y, whereas O is the union of balls in X, in the bigger space X. So O is a union of open balls, as a union of open balls is an open set. And it's straightforward to check that O intersected with Y is precisely A. So when I intersect this union with Y, I get precisely this, because by distributivity of intersection with respect to unions. So this proves the proposition. And now let us illustrate this by some examples. So equip R with the usual distance and consider, so we take capital X equal R, and we take capital Y to be half the line, 0, infinity, closed. Now, if we consider, so we take capital A here, 0, 1, semi-open at 1. So open at 1, closed at 0. This is A. So this is X, Y, A. Now, 0, 1 is not open on R, we know that. But it's open in the smaller space 0 plus infinity. Why? Because, for example, we can write that 0, 1, A is equal to 0, infinity, Y, capital Y, intersected with this open interval minus 1. And here we see that the set O is not unique, because we can write 0, 1 is equal to 0, infinity, intersected, for example, with the interval minus 1/2, 1, or minus 1/3, 1. So it's not unique. Okay, so it's very important to distinguish between when we talk about open sets, we have to precise with respect to which topology or to which subspace. Okay, another example, we take capital X equal R and capital Y equal the set of integers Z. Okay, now every singleton, so this is actually capital A, so take n in Z and take capital A to be the singleton n. We know that the interval n minus 1, n plus 1 intersects the integers only at n. Okay, so it follows that the singleton n is open in Z because it's the intersection of an open set in R with Z. And of course, this is not unique, because you can write also as n minus 1/2, n plus 1/2, if you like. So therefore, every singleton is open in Z. And it follows that, therefore, every subset of Z is open in Z, because every set is a union of singletons. And therefore, every set is also closed in Z. So all the sets of Z, subsets of Z, are both open and closed. Okay, this illustrates the fact that a set can be both open and closed. Okay, other than the whole space and the empty set. Okay, so this may be confusing for the first time, because so once again, the singleton n is not open in R. I'm not saying that, but it's open in the smaller subspace Z. Okay, so corollary, if now Y is itself open in X and U is open in Y, then U is open in X. This is straightforward, because so here I just changed the notation. So instead of A, I took U. But so if U is open in Y, by the previous proposition, we can write U as the intersection of Y with an open set of the bigger space X. If Y is open in X and V is open in X, the intersection is open in X, so U is open in X. So this was not the case here, because 0, infinity is not open in R. This is why 0, 1, semi-open is not open in R. Okay. Now, what about closed sets? We have a similar characterization. So once again, if we have a metric space X and a subset y of x and the subset again a of y, then A is closed in y if and only if A is the intersection of y with a closed set of the bigger space x. Okay, so two implications. So suppose first that A is the intersection of y and the closed sets in x. Then the complement of A is the complement of, in y of course, of y intersected with f. And now, by elementary set theory, this set y without y intersected with f is just the intersection of y and the complement of f. Okay, how do you prove that? You can do double inclusion or equivalence, because a point is here, x, small x, if and only if it is in y, but not in y and f. So it's in y, but not in f. That's it. And now, if I let O to be the complement of f in x, if f is closed in x, then O is open in x. And we can write y without A is therefore y intersected with O. So by the previous proposition, y without A is open in y. Therefore, A is closed in y. Conversely, suppose that A is closed in y. We want to write A as the intersection of y and f. Okay. So I deduce this from the previous proposition. So if A is closed in y, then the complement of A in y is by definition open in y. So we can write y without A as y intersected with O, okay, by the previous proposition. Again, we use it twice. Okay, so therefore, A is the complement of y intersected with O, complement in y. Okay, and once again, this is y intersected with the complement of x in O. So if I let x without O, I denote the set by capital F, then F is closed in capital X because it's the complement of an open set in X. And we can write A as the intersection of y and F. Okay, so this concludes the proof of proposition 1.15, and let me end by an example. If we take y equal the open interval 0, infinity, and A is the semi-open interval 0, 1, open at 0, okay, and x, capital X equal R. Then 0, 1 is not closed in R as we know, but it's closed in this smaller space because we can write 0, 1 equals 0, infinity intersected with the closed interval 0. And we can also write it as 0, infinity intersected with minus 2, 1 or minus 1, 1 closed. So it's not unique. Okay, so this illustrates the concept of relative openness and relative closedness. And as a corollary, if y is closed in x and A is closed in y, then A is closed in x because of this, because we can write A as the intersection of two closed sets in x. Okay, and once again, this was not the case here because 0, infinity is not closed in R. Okay, so I know that this may be a little bit confusing, but you can watch the video several times. And so thank you for your attention and see you next time.